Okay, good morning. Welcome to Physics 4B. I'm Frank Coscarano. You can call me Frank. You can call me Mr. Coscarano, whatever you're comfortable with. It's okay with me. So 4B, let me start off by, hopefully you're familiar with Zoom by now, but there's the chat box. That's probably the best way to ask a question during the lecture. There's also, if you look down at the bottom, it says, let's see, under participants, there's a way to raise your hand or give me a thumbs up under reactions or something like that if you're have a question or you want me to slow down. Anyway, there's some feedback mechanism there. Thumbs up, thumbs down, if you're getting it or not. Go faster, go slower. Anyways, there's some feedback buttons there you can press, and hopefully I'll see those. We have a lot of participants though, so I might not. You might have to do it a couple of times. Okay, chat box, I'll try to monitor that as we go, and hopefully everything's going fine here. Maybe we should practice by giving me a thumbs up if you can hear me okay and see me and all of that. All right, I'm seeing a couple of thumbs ups. Excellent. Oh, there we go. Lots of them. Okay, good. Thank you. All right, so let's see. Let me share my OneNote with you, so hopefully you can see that. Let's share now. Oh, there we go. There we go. All right, so I'll write on OneNote, and so this, I'll just use this like I do the board. I'll write here, and then at the end of the day, I'll make a PDF of this file and post it on the website. And also we'll record this, and this will be posted somewhere. So if this is not a convenient time for you, you can watch the lecture at another time. But we have a lot of people, which is good because we want it to be interactive. We want you to be able to ask questions. I think you'll get more out of it if you can do that. All right. So I'll tell you a little bit about myself, and then we'll get started. I went through school as a physics major. I went to Davis, UC Davis, and then got a bachelor's degree in physics, and then went on to get a master's degree at UC San Diego. And when you go through school as a physics major, people always want to tell you how much they hate physics. I don't know why. They feel compelled to tell you how much they hated physics. So I hope that's not the case here. Physics is tough. I know that. It might be the hardest class you ever took, but something has to be, right? But I hope you'll at least see what physics has to offer, and you appreciate what it has to offer, because it really is. Physics strives to explain the world around us. And that's pretty interesting. There's a lot of neat stuff around us all the time. This week we'll learn how a photocopy machine works. I don't know if you've ever really thought about it before, but it's pretty amazing, and it's just electrostatics, and that's what we start off with this week. So a lot of interesting applications all around us, and I hope you'll at least appreciate that. Whether you run to the registrar's office and change your major to physics or not, well, that's another story, but I hope you at least appreciate what physics has to offer. So I went through school as a physics major, then I worked in the semiconductor industry for 10 years doing what's called process engineering. So we had a machine that deposited an electrically insulating layer onto a silicon wafer. So a silicon wafer goes through about 300 different process steps. You're depositing different types of films on the wafer, you're removing some of those films, you're creating patterns. So depositing, etching, creating patterns over and over again, about 300 times before you're ready to cut that silicon wafer up into computer chips and package them and make computer chips out of it. And our machines did a few of those jobs. So most of the time I worked in the semiconductor industry, our machines deposited an electrical insulator onto the wafer. And so my job was to optimize that film that we were depositing. So tweaking the times, the temperatures, the ratio of the chemicals, things like that to try to optimize the film properties. So I always tell people it's a lot like cooking, right? What does a chef do? They try to optimize the taste, the texture, the look of the food. And that's what I was doing with these films. And I like cooking too, so I guess there's some synergy there. And I did that for 10 years, and then I found I was always drawn to teaching roles within the companies I worked for. So I decided to make that change permanent, and about, 15, 16 years ago, I started teaching, and so I've been doing that ever since, and I couldn't be happier. All right, so that's me. I'll tell you a little bit about the class and study habits. So one of the things that physicists like to do is test things. And about 20 years ago, 25 years ago, they started testing how well we're doing at teaching physics. And what they found is that we're not doing a very good job teaching physics. So a lot of work has gone into this field. It's called physics education research. There are a lot of physics departments that have PER divisions, physics education research groups within them. And then they study all kinds of things. And one of the things they found was that physics is just a little tricky because our everyday experiences are sometimes counterintuitive to the underlying principles. As an example, let me give you a simple example: friction, right? So one of the first things you learn in physics 4A is you push on something and it's going to keep going forever until a force acts on it. But every day, every time you've ever pushed on something, it's come to rest, right? It doesn't keep going forever. So that's one of those things that our everyday experiences and intuition gets in the way, and it's clouded. The underlying physics is clouded by the fact that we have friction and air resistance and things around us all the time that we can't really get past. So that's sort of a simple example. But even in this class, even in Physics 4B, you might think, well, I don't have any experience with current in a circuit or electric fields. But studies show that it doesn't matter whether you have experience or not. You've got some ideas about how these things work, and there's a good possibility they're wrong. So what we have to do is kind of break down some of those beliefs that students come into physics class with and try to get you to see things from a right fundamental perspective so that you can build on that and grasp what's going on. And so a lot of the activities I do, I call them worksheets, but you probably won't see them as a worksheet in this format, but I'll have exercises that we do in class and things that are really designed to break down some of those preconceptions that people have and get you to see things the right way. So that's one. And the other one is just sort of the lecture style is really not a good way to learn something. A lecture is a really good way to disseminate information to a lot of people quickly. I can stand up in front of a room and say something, and 60 people just heard what I said. But it's not a very good way to learn something. So we'll stop periodically. I mean, in this format, again, maybe it's good, maybe it's not. I don't know. We'll see. But we'll stop. I'll try to have you do some exercises, pause the video, have you do some exercises, we'll come back, we'll talk about it, things like that. And so the more you participate, the more you try to get out of these 2 hours that we spend together, the better off you're going to be. Okay. Now, that brings us to study habits. There's a couple of books I'm recommending. The first one is A Mind for Numbers. If you want to read that and write a little summary of it and how you're going to use that material to make yourself a better student, then I'll give you some extra credit. That went out in the email. Hopefully you saw that. And if you've already done A Mind for Numbers, there's a second book listed there that you can do Thomas Frank. He's on YouTube. He's got a YouTube channel. Check him out. He's got a lot of the same information as in the other book, but he's got his own way of saying it. So check it out if you've already read A Mind for Numbers. So a lot of the things talked about there, we just spent 2 hours in class going over stuff. Some of it's in your mind there. You're working on it. Maybe it's not all crystal clear, but you've learned something, hopefully. Well, if you wait too long, if you wait till the weekend and you decide, I'm going to study physics on the weekend and get this straight, you've lost it. You've wasted that 2 hours. You're going to have to relearn that material. But if sometime later today, you spend an hour going over your physics notes and the problems we did in class and try a couple of extra problems from the sections in the book that we covered today, then you're kind of locking in that information, and that's going to just save you a lot of time. Physics is going to take a lot of time anyway. So the more efficient you can be in your studying, the better off you are. So a little bit every day, much better than a lot on the weekend, right, or one time. What else study habits? The book has a lot of things. They have suggestions for dealing with procrastination and things like that. What else did I want to say about study habits? So I think that's one of the most important things. The other important thing that is talked about in the book is that you want to come in. We've got these 2 hours here. We want to get the most out of this 2 hours of time we have together. You want to learn the most in these 2 hours so you can spend less time outside of class learning the material, right? And that means that you want to come into class primed and ready to go, having seen some of the material before, having heard the concepts. And the first time you see something, if it's laid out nicely, it kind of makes sense. You go, oh, okay. Then you go home and you open the book and you try to attempt it yourself and you can't do it, right? So you want to get to that point before you come to class. You want to get to that point where you get stuck, and then you come into class, and then we can get you through that point where you're stuck and you've learned something and you get a little bit more out of lecture that way. So that's important. Come in primed. Those lecture worksheets, if you checked out my website, they're called the lecture worksheets. There's one for every lecture, and it gives you some suggested. I'm not going to collect any of that, but it gives you some suggestions. So do the pre-lecture and the pre-lecture and the post-lecture, and that's all good stuff. The pre-lecture will get you primed for what you're going to see that day. Hopefully, sometimes I get off a little bit, but pretty close. The goals for the lecture, go back, review those, make sure you got it. And then at the end of the day, after class, later on, go back, look over the pre-lecture stuff, make sure you can answer those questions. Go over the post-lecture things, make sure you can answer those. And that's all feedback, right? That's feedback you're getting every day. You can do the post-lecture stuff. If you can do the in-class assignments, go back over those. That's feedback every day you're getting. And if you can't do something at the end of the day, fix it right away. Don't put it off. Physics builds on itself, and we have a lot of material we have to cover. So don't get behind. You won't be able to catch up. As soon as you hit something that's giving you trouble, that's okay, get help right away. And I'll set up, I haven't sent out the links with the office hours. I will do that later today, but I plan on having an office hour every day from, 4 to 5, I think it said. So hopefully that works for you. If anybody has issues with times and things, please let me know. And send me an email or use the inbox in Canvas, whatever's easiest for you. Question about homework problems assigned from the textbook. So the answer is yes and no. I do have homework problems assigned from the textbook. I don't collect them though. Well, really what they are, they're suggested study problems. So what happens is you turn that book to the end of the chapter and you're overwhelmed. There's 100 problems at the end of the chapter. And so, sometimes that leads to procrastination, right? You don't know where to start. You're overwhelmed by the back of the book there. So my suggested homework problems are there to give you a little push and say, okay, do these 20 problems first. And so just start checking them off, start doing them, checking them off. And after you do them, sometimes there's about 20 problems there, sometimes there's more. After you do those problems, then you say to yourself, hey, am I getting it? Can I, if I sat down with a problem similar to this in an exam situation, would I be able to do it? Or do I need more practice? You know, if you need more practice, there's still another 80 problems in the back of that chapter probably, or maybe you can find another textbook if you like the problems in another textbook better. But you have to work a lot of problems. What I put on that suggested homework problems on the website, excuse me, that is just a minimum kind of to get you going. Hopefully at the end of doing that, you've got some confidence and you feel like you can answer those problems. But if you don't, then work more problems. Yeah, I don't collect any of that. I would not call it optional. If you want to pass the class, it's absolutely mandatory, but I don't collect any of it. Okay. So study habits, I think we've covered some of that. I don't want to spoil the reading of the books for you, but I think I gave away most of what's in those books. No, no, there's good stuff there. There's, like I said, hints for procrastination, other study techniques that are good. And then they're easy reads. These books read pretty quickly and easily. So anyway, I think you'll enjoy them, and I think they'll help you out. That's why I'm suggesting it. Okay, very good. So what we're going to do here, question about math knowledge that you need to use. So we do this, physics 4b is probably the most math intensive of the physics sequence. We do a lot of integration, but they're only single integrals. So that's my deal with you. I won't give you any double or triple integrals you have to do. So the it could get oftentimes we are integrating over a charge distribution to find an electric field. Well, if the charge distribution is one-dimensional, right, just a line of charge, it's a single integral. If the charge distribution is two-dimensional, right, like a disk that's got charge spread out over the area of the disk, then you have to integrate over the area of the disk. It's a double integral. And if your charge distribution is throughout a volume, like maybe a sphere, throughout the sphere, the volume of the sphere, you have charge everywhere in that sphere, you would have to do a triple integral, right? You'd have to integrate over the volume and add up all the contributions from the different charges. Well, for the purposes of this class, I will only give you one-dimensional charge distributions, so single integrals. And as you get the math techniques, it's the solving a problem that you have to do a double integral is not really that much more difficult. So I think for as far as the physics is concerned, show me you understand that on a one-dimensional charge distribution. Okay, excellent. Okay, so let's get started. Oh, a couple of other things I wanted to do. A question about using a different textbook. Yes, I'm okay with that. In fact, I would say that the one issue I have with our online textbook is that the end of chapter problems are a little weak, I think, on some topics. So most of them, I think they're okay. There are a few that are a little weak. So if you have another textbook, anything that says university physics, if it says college physics on the cover, don't use it. There's no calculus there. If it says university physics, you can use that. Or if it says physics for scientists and engineers, something like that, those are good books to use. Any one is fine. If you want to pick up an old edition, you know, like Survey is a book that we've used here at Foothill in the past. And I think they're on their 10th edition now, 9th or 10th edition. So find the 7th edition for a few dollars somewhere. Of course, with the shipping slowdown now, and you might not get it in time. But any cheap old book you can find, as long as it says scientists and engineers or university physics, it'll be fine. It's always good to have a source of extra problems. I was going to say something. Oh, timing and things. I'll send out another email with links for the office hours, things like that. But what I want to do today, and I'll probably remind you one more time right before we end our lecture today. But what I'll do is I'll try to run this the same way I would in class. We'll stop about halfway through for a 10-minute break, stretch our legs, things like that. And then I think I'd like to start the lab at 12:15 instead of at 12. That way you have a few minutes. So you're not going 5 straight hours of physics today. You have a 20-minute break or so, 25-minute break to grab lunch or stretch your legs or just take a mental break from physics, and then we'll start in with our lab. We will have a lab today. It's on uncertainty, and I've posted the lab handout to the website already. So we'll do that, and I'm expecting about half of you today and about half of you on Wednesday for the lab. And I don't care which lab you come to. If you're registered for the other one, but today's is more convenient, that's fine. As long as you're registered for the class and you come to a lab, I don't care which one. And let me know if you have any issues with timing there too. Okay, send me an email. All right, so I think we're ready to get started. Any other questions? Let me see, physics or scientists and engineers. Yeah, any lab is fine. Email me and I will send you, I think everybody that's emailed me, I have sent an ad code to, and I believe the ad codes now work. I've never handed an ad code out before the first day of class before, but apparently they don't become active until the class starts. So today our class started and my other class starts tomorrow. So that the ad codes for that class won't start until then. Okay, if you're having any issues, just email me and I'll try to get you taken care of later today. Lab classes. So labs, we've given it some thought. We've checked out a lot of online resources and things. And what I think we're going to do is, for the most part, I will do the lab in front of the Zoom camera here, like we're doing this. I'll set up the lab here and I'll do it, and you'll be just observing and writing down data and things like that. So a lot of the labs will be the exact same lab you would have done at Foothill. Instead of you actually touching it and doing it, you're just watching me set it up and recording the data and doing the analysis. So that's a number of the labs will be done that way. There are 1 or 2 that we're going to use the PhET simulations for, particularly for circuits. The simulations are very good for the circuits, and you can set that up and do that just the same way you would in class, but you'll be using the simulation instead of actual resistors. And if my plan for the lab is to do them like this. So because I'm sort of walking through the experiment and you're taking data, I think we all need to be logged in at the same time. So right now I've got them scheduled for the exact same times that we would have met in person. So today after class, right? Today and after class on Wednesday. If that's a problem for people, then I'm willing to change one of them to another time. But nobody's contacted me yet. So I'm assuming everybody's okay with making these 2 times. So if you have an issue, let me know. and we'll try to work something out. My thought process was that if there were enough people, if I had 20 people that wanted a different time, then I would just change one of the lab times to a different time, and hopefully that would work for everybody. People that wanted the afternoon lab could take whichever one we keep, and the other one we move to an evening or something. But anyway, nobody's emailed me. So right now, the schedule is we just meet at the normally scheduled lab times. Pick one that works for you, and we'll go through things. Okay? They're going to be done, the labs will be done individually. Labs will be done individually, and we'll upload those into Gradescope the same. Everything that's graded will upload into Gradescope. I think that's just to keep it simple. The recordings of these lectures, I believe I can put a link from my website. That's my plan. I'll probably upload them to YouTube and then put a link on the website. Somebody is telling me that they would be interested in a different time. So maybe you can use the discussion board in Canvas. There's the one there for general questions or something. Maybe you could use that to start a thread about people that might be interested in an alternative time, or email me and then I'll keep track. Okay. Ready to start electricity and magnetism? All right, so as you're probably aware, we have two types of charges. And for some reason, they came up with the name positive and negative to describe those two types of charges. And we know that they come from within the atom, right? So our atom has a nucleus that has positives and neutrals in there, right? So the positives are tied to the nucleus. Those don't move, right? That's part of the nucleus. If a positive moves, then you don't have the same atom anymore, right? You change the number of protons, it's not the same atom anymore. And there's this cloud of electrons around the outside. So for most of the time, we have the same number of negatives as we have positives. So we have neutral atoms. Most things are electrically neutral. Now, what happens when things rub together? Some materials hold on to their electrons a little bit tighter than other materials. So as dissimilar materials rub together, the ones that hold on to their electrons tighter will steal and grab some of the electrons from the other material. So if a material gains electrons, it becomes negatively charged. If it loses some of its electrons, then you can see right here, it now has more positives in there than negatives because it lost a couple of those electrons on the outside. And so now it becomes positively charged. So we don't add positive charges to something to make it positively charged. We remove electrons to make it positively charged. And we add electrons to something to make it negatively charged. And the most common way of charging things is just they rub together. Dissimilar materials rub together, and some end up grabbing onto electrons and holding onto them faster, stronger, and hold more steadily than the other ones. And you can just look it up in your chemistry textbook or go online, look up triboelectric series, and you'll see what the materials are and which ones will steal electrons from other ones. And so you can check that list. And we know that like charges repel, and opposites attract. Okay. So if we have two like charges, doesn't matter what they are, the force is away. Excellent. And we have opposite charges, the forces are towards each other. Protons are positively charged. They make up the nucleus of the atom. They never change, right? That if you remove a proton from an atom, it's not the same atom anymore. That's how we determine what an atom is how many protons it has, right? If that's placed in the periodic table, it's determined by how many protons it has. So that's a fixed number. That never changes. The positive charge never changes. But that cloud of electrons that is around the outside of the nucleus, that can change. We can pluck an electron off of that cloud, and it can become positively charged because there's less electrons, or we can add an extra electron and it becomes negatively charged because there's more electrons than protons. Okay. So I'm going to trying to do some demonstrations for you. So I videotaped them. Let's see if we can do this. I have to share this. Hold on just a second. I want to share this one. Okay, here goes. We'll just run through a few of these quick demonstrations. There we go.
Here I'm electrically charging a balloon by rubbing it with a piece of wool. Now I'm going to rub a PVC pipe with the same piece of wool. Both of these objects, the PVC pipe and the balloon, have the same sign charge. In this case, both are negatively charged. What can we say about like charges?
Okay, I think we're good with that, right? These two obviously repel. The force of gravity wants to pull that balloon to the ground, but the electric force between these is pushing up, and we can get it to float like that. Okay. Let me jump to the next one. So I can write on here, okay, next one is, yeah, I think we'll cover some of the questions that are coming up, but if not, ask me again. Okay, here's the second one.
This is an ordinary balloon. What's going to happen after I rub it against my hair?
Okay, so we've all done that, I think. The balloon and the hair interact with each other. The hair becomes positively charged. The balloon becomes negatively charged, if I remember correctly. Now we have a charged balloon, and my hair is oppositely charged, and so opposites attract. Okay, let's keep going.
Now I'm going to take that balloon and hold it up to the wall. That wall is an electrical insulator. Stop the video and predict what's going to happen when I let go.
Okay, so think about that for a second. We've probably all done this. But that balloon is charged. I rubbed it against my hair. It's charged. And we're holding it up to the wall. And most of us have done. Not everybody's done this, I guess. So let's see what happens.
As you probably knew, the balloon sticks to the wall. Now I'm going to take the balloon and hold it up to this aluminum pie plate. That's an electrical conductor. Pause the video and predict what's going to happen when I let go of that balloon.
Okay, so the wall is an electrical insulator, and it's stuck to the wall. This is an electrical conductor. I guess not everybody's done this. Oh, actually, I have a poll. Wait, let's try this. Where is it? Where is it? I set this up. I forgot I set up a poll for this. Here we go. Poll. There it is. Sorry, I have to launch it. So there's a poll. The first question is, well, we've already done the first question. I forgot to launch the poll. Charge the balloon up, hold it to the wall. Yeah, okay, we all know what happens there. We saw it. Now we're charging the balloon up and holding it up to the pie plate. So go ahead and think about what's going to happen. Okay, about 2/3 of you have responded. Okay, I'm going to end it now. I've got 90% response. I guess that's okay. End the poll. I'll share it with you. So it looks like people think, where are we? Scroll down here. A few people said they'll attract. Quite a few more, about a quarter of the people, 37% said they'll repel. 18% no interaction since the pie plate's neutral. And the largest response, just slightly by a percentage point, they attract for a moment and then the force goes away. So let's take a look. Are we ready? Okay, so here goes.
That electrically charged balloon is attracted to the conductive pie plate. It was also attracted to the insulating wall. The charged balloon is attracted to the conductor and the insulator.
Okay, let's talk about it. Let's see, I got to share my. Oops, what happened? There it is. Okay, so we had in the first case here, like charges repel. Now we're seeing the balloon sticks to the wall, sticks to the conductor. Let's think about what's going on there. So we've got our balloon. We've got our wall. There's our balloon. We'll make it, what charge? I'll make it negatively charged. Negatively charged balloon and the wall. So a wall is an electrical insulator. The charges can't move around. That's the definition of an insulator. Those electrons are tied to the atom that they're surrounding. They can't move around from atom to atom in the substance, in the material. In a conductor, the electrons are not held to each atom. They're not tied to the atom. They're free to move around from atom to atom. So if a conductor is electrically neutral, then there are the same number of protons as there are electrons, but the electrons can move around from atom to atom. In an insulator, they can't. They stay right where you put them. They're tied to the atom that they come with. So when you bring that negatively charged balloon up, we know that the electrons are repelled. Electrons are negatively charged. They're repelled by that balloon, but they can't move very far, but they can shift a little bit. So if my atom is surrounded by an electron cloud, that electron cloud can shift a little bit one direction because of a big negative charge over here. It can shift a little bit, repelled. And so the atom becomes what we call polar or polarized. So the atom, even though the electrons are tied to it, shifts, the electron cloud shifts. And so here's the atom at the surface of the wall. The electron cloud shifts a little bit so that one side of the atom is positively charged and the other side is negatively charged. And all the atoms here in the surface do that. And the next set of atoms, I'm zooming in very close on these atoms, right? So here's our non-conductor. I gotta set my hand down. Okay, so what ends up happening is the surface becomes slightly positively charged. And all this stuff back here kind of cancels out. And that slight positive charge at the surface causes the balloon to be attracted to the surface. So somebody asked earlier what happens with a neutral. Well, this is what happens. You can get a charged object to be attracted to a neutral object because of this effect. Now let's see what happens with our conductor. So we have our negatively charged balloon. I should probably, my drawing skills are not very good. I have to tell you what that is. There we go. That's a balloon. And we have our pi plate now. And what happens is the electrons in a conductor are free to move around. And we bring that negatively charged balloon up, And the electrons want to move away from that. And so we get an electron that moves over to here, and we get an electron that moves down to there. And what's left behind are some positive charges, right? So the electrons, they don't just shift a little bit, they move to another part of the conductor. And so we're left with positive charges behind, and we get a nice attractive force there. Let me check the chat box here. How do you figure out which one is positively charged, which one's negatively charged? When you rub items together, you have to look at the triboelectric series. So check your chemistry book or just Google it, and you'll see there's a list of, in order, of which ones are more likely to steal electrons. So if you have one down at the bottom of that list that's really likely to steal an electron, and you rub it against something at the top of that list that's more likely to lose an electron, then the one up here, the hair, human hair, is kind of at the top of that list for losing electrons, and rubber is down towards the bottom. So the rubber gets picks up the electrons, becomes negatively charged. Your hair becomes positively charged. I think is the way it works, but I haven't looked at that in a little while. Okay, hold on. Let's see, where were we? Yeah, the conductor should be a stronger attraction than the wall. Oh, okay. So I think one of the things that's coming up here is probably because the balloon, and maybe this was one of the things we were thinking about earlier, the balloon is an insulator. So if the balloon was a conductor, if I had a conductor, and I held it up to a conductor, then what happens? These electrons can move. These electrons here are all repelling each other. They want to get as far away from each other as they can. So some of them are going to move and go away, right? And so very quickly, if this is big enough, if this conductor is big enough, these electrons will all move, and we'll be left with a neutral conductive sphere instead of a charged conductive sphere. They'll all move over there to get as far away from each other as they can. But the balloon is not a conductor. The balloon is rubber. It's an insulator. So maybe right here where the balloon is touching, maybe right there, a couple of electrons moved over, but the rest of that balloon is not touching the wall. And so those other charges, they're stuck there. Those other electrons are stuck on the surface of that balloon, and they can't move across. And so that's why it retains its charge. What ends up happening over time, if I put that balloon against the wall today and we came back tomorrow, it probably wouldn't be there. It probably would fall down because there's a lot of dust particles in the air, and a lot of the dust particles in the air are actually electrically charged, slightly charged. And so if the balloon is negatively charged, it's going to attract positively charged dust particles, and they will neutralize that negative charge eventually, and it will lose its charge over time and fall off the wall due to the charges in the air. We good now? So since we're talking about this right now, let's just finish up on this and then we'll take a little break. So actually, I've got 2 more videos to show you. Okay, so let's do this one. Let's do these last 2 videos and then we'll take a break. 5. Okay, here goes. Okay, you thinking about it? Let's see what happens.
Excuse me, Professor.
Yeah, go ahead.
We're not able to hear audio from the video. Were we supposed to be able to?
Okay, hold on.
Thank you.
Thank you. I'll tell you what, I'll give you the audio. Okay, so the rod is electrically charged. The aluminum can is electrically neutral. And they attract each other. So the aluminum can is a conductor, but it's electrically neutral. And it doesn't matter if it's a charged rod or a charged balloon, any charged object does the same thing. Okay? And so that's what we just talked about. Where's my I have to share? So that's what we just talked about here. It doesn't matter whether that object is a conductor or an insulator. We can get this attractive force either way. So with a conductor, what happens with that aluminum can? You bring the charged rod over here, and the electrons in the aluminum can move to the far side of the can, and that leaves positive charges on this side, and we get an attractive force. Even though only one of those objects is electrically charged and one is neutral. Okay, let's watch one more video and then we'll take our break. Let's let me share it with you.
The small pieces of paper are electrically neutral. The PVC rod is negatively charged after rubbing it with the wool. What's going to
happen? Those pieces of paper are electrically neutral.
See there's no video.
There's no video.
Thanks, Brent.
There we go. Thank you.
The small pieces of paper are electrically neutral. The PVC rod is negatively charged after rubbing it with the wool. what's going to happen to those pieces of paper?
Okay, hopefully you can hear that. Those are small pieces of paper. They're electrically neutral. We have an electrically charged rod. Let's see what happens.
Pause the video and make a prediction. The small pieces of paper are attracted to the rod. But let's watch again in slow motion to see what happens after they touch the rod. After touching, they repel each other.
Okay, we're back to our my OneNote page here. So let's talk about that real quick. We knew the balloon stuck to the wall, and we knew the balloon stuck to the pie plate. So that should tell us that the balloon is going to attract the aluminum can, and the charged rod is going to attract the pieces of paper, right? So those pieces of paper become polarized. You bring your charged rod and your little pieces of paper then become polarized. So you have that positive, negative, positive, negative. The atoms, right, move. The electron cloud, those pieces of paper, of course, are electrical insulators that electrons can't move. But the electron cloud can shift a little bit and make the top slightly positive. And closeness counts in electricity because those positives are a little closer. Yes?
Something happened just now. Okay, it's back. Weird.
Your audio got turned way up.
Oh.
Yeah, it made it real.
Yeah, it sounded like you were speaking directly like into your mic, and you sounded insanely loud for about 3 or 4 seconds. Sorry.
Okay. Sorry about that. We're good now? Sounds like we're okay now.
Yeah,
Okay.
we're
Yeah,
fine.
you're-
Sorry.
Okay, good. All right, no problem. No problem. We'll figure this out. I ordered a good microphone, but it won't be here for another couple of weeks, so I'm stuck with this one. But so far, so good, I think. All right, so our pieces of paper become the surface becomes slightly positive because of the shift in the electron cloud, and we get an attractive force. And it doesn't matter whether that rod is positively charged or negatively charged, you always get an attractive force. So when you see an attractive force between two objects because of an electrical charge, they don't both have to be charged. One of the objects could be neutral and the other one could be charged, and you will get an attractive force. But if you see a repulsive force, they have to both be charged. You will never get a repulsive force because of this. So once those pieces of paper touch the rod, then an electron might jump across. It might pick up an electron. Now you have two negatively charged objects, and like charges repel each other. Okay? Yeah, because where the paper is actually touching, at that point where the paper is touching the rod, you can get transfer of charge. There has to be contact, there has to be touching. But the paper is small enough that it comes up and touches in 1 or 2 points, picks up an electron or two, and then that's enough, at that point, that's enough of a charge to make them repel each other. Because the effect from the polarization of the atoms is very small. So once something becomes charged, usually that dominates. Okay, so I went about 10 minutes over, but that's okay. We'll stop the video now. I'm going to pause the video and we'll take a 10-minute break, stretch your legs, get the blood flowing, and I'll try to scan through and see if I missed any questions, and then we'll pick it up again in 10 minutes. All right?
Professor, can you hear me?
Yes.
Oh, before you leave, so you emailed me an ad code before.
Okay, hold on
class
just a second. Let me pause. Pause. Okay, I've added a few notes to my drawings to hopefully that'll help a little bit when you go back and look at those later. Okay, a few questions in the chat box. One is conductor or insulator, anything can gain extra electrons. That's correct, right? We can have an insulating material and we can electrically charge it. We can have a conductive material, we can electrically charge it. Either way, you could end up with a charged object, electrical insulator or electrical conductor. We can charge either one of them by adding or removing electrons. Okay, so does the PVC attract because the paper is charged? So the point of the video we just watched was that the pieces of paper, the little white pieces of paper, were electrically neutral. And they, when you hold up, let's go back up to the balloon here earlier. When you hold up the charged object, so here's our charged object, next to an insulator, in this case it was the wall, down here it was the pieces of paper, but it doesn't matter. Anytime you have a charged object and an insulator, the atoms that make up the insulator, the electron cloud shifts a little bit and the surface becomes oppositely charged. Whatever the object is that's charged. In my case, I wrote it as a negatively charged object, right? The balloon was negatively charged, the rod was negatively charged, but it doesn't matter. You can go through it later in your mind, think about what happens if that balloon is positively charged instead, and you should still get an attractive force. So in my case here, I wrote negatively charged. It pushed, I bring in a negatively charged object, it pushed the electron cloud away, the surface becomes slightly positive. Positive and negative attract. Closeness counts in electricity. So the positives are a little bit closer than the negatives, and you get an attractive force. And that's what happened here with the paper. We got an attractive force. The atoms and molecules, it's an insulator, so the electrons couldn't move away like they did with the aluminum can, but they could polarize a little bit and make the surface slightly positive, and that caused the paper to attract. Once the paper touches, some electrons move, and it doesn't matter whether that rod is positive or negative. If the rod is negative, it has extra electrons, and they want to get away from each other. Those electrons are all repelling each other. They want to get away from each other, and a piece of paper touches it, and an electron says, oh, I can move and join that piece of paper and get away from these other electrons that are pushing on me. And so one or two electrons, wherever that piece of paper touches the rod, transfer over. Now you have two negatively charged objects and they repel each other. And if the rod was positively charged, the electrons would go from the paper to the rod. They would be attracted to the rod. Either way, the electrons move, you get some transfer, like charges repel. Okay? Good. And then it says, what does it say here? Yeah, insulators can gain electrons, insulators can lose electrons. Yes. Okay. So let's take a look at this situation. Two uncharged metal spheres. Question about insulators. So in an insulator, the electrons cannot move around from atom to atom. They're tied to the atom they're with, right? They can't move around. In a conductor, the electrons can jump around, move from atom to atom within the conductor. In either case, if we have an insulator, the electron cloud is tied to one atom. But if we rub another material across it, we could steal an electron from one of those atoms, and now that atom has fewer electrons than protons, and it's now positively charged. Good? So they can grab electrons or lose electrons. Either way, depends on what rubs against it. Okay, so what do we have here? We've got our two metal spheres. So these are uncharged metal spheres. They are conductors, and they're isolated. We bring up a charge, they're touching each other. We bring up a charged rod, and then we remove that charged rod, and then we separate the two conductive spheres. What's the charge on each sphere after we go through this process? That's the first case. The second case is we bring up the charged rod while the two spheres are together. Then we separate them while that charged rod is still there. And then we remove the charged rod afterwards. You understand the difference? So in the first case, the charged rod comes in, and then it goes out, and then we separate these afterwards. And in this case, the charged rod comes in, then we separate these while the charged rod is still there. Then we get rid of the charged rod at the end. So think about that for a second. And I will give you a poll. I made a poll for this. Where's our Zoom? Where's my next poll? So question number 1 is the first case, and question number 2 is the second case.
Professor,
Yes.
are the answers for question 1 and question 2 the same? Are the options the same?
Options are the same, yes.
Okay, thank you.
All right, thank you for helping out in the chat box. I appreciate all the responses. Okay, I'm going to end this. And we'll see. So in the first case, most people said that they both remain neutral. And that's correct, because what happens is you bring in the charged object. While that charged object is there, we get some extra electrons move. What's going on? Oh, there we go. Some extra electrons move over, and what do they leave behind? Positive charges. But then when you remove this, those electrons want to get away from each other. They want to go back, spread out as evenly as they can. And so you end up with both of these being neutral. Now let's take a look at the second one. Most people said number 9. Let's take a look at that. So here, you bring in that charge. Electrons are attracted to this surface that leaves some positives behind. Now you separate them. So the one on the left, sphere 1, has some extra electrons. And the one on the right has some extra positive charge, or a lack of electrons, if you prefer to think of it that way. And so we end up with the situation outlined in 9 there. Charge object 1 here is negatively charged, and 2 is positively charged. So both cases, the spheres are eventually separated. In the first case, they were separated when the charged rod was not present. In the second case, they're separated within the presence of that charged rod. Okay, so let's talk about forces. Because we've sort of been alluding to the fact that there are forces here, right? So for our cases here, electrons, I'm not sure what you mean by jump. There's a question about electrons jumping. There has to be contact. For our class here, there has to be contact for electrons to move. So what happens sometimes in the real world, there's a spark can form, right? Electrons can move through the air from one object to another because the air breaks down and becomes a conductor, okay? So if the charge difference is so big between two objects, if I have an object that has lots of positive charge, an object with lots of negative charge, then the air molecules in between those two objects, air is normally an electrical insulator, but the electrons will get pulled in one direction and the positives get pulled in the other direction. And if the electric field is so strong, if I have enough positive and negative charges there, as they get pulled, it can actually rip an electron off of one of the atoms and molecules that makes up the air. That's called ionization, right? We've removed an electron from it. We put it in a really strong field, and the positive wants to go one way, the negative wants to go the other way, and we've ripped an electron off, and now the air has broken down and become a conductor. And that's what a spark is. That's what lightning is, okay? We're not going to deal with that right now. So for our purposes, when electrons move from one object to another, there has to be contact. They have to be physically touching each other. We assume that air does not break down. Air is an insulator for almost everything we do here. Okay. And so because this rod is positively charged, it attracts negative charges. It attracts electrons over to it. And then we separate the rods. One has to be negatively charged and two has to be positively charged. If we had a negatively charged rod there instead, then of course the answer would be reversed, right? One would be positive and two would be negative. Okay. Okay, the spheres started out touching. The spheres started out touching each other. So electrons, it was like one big conductor, right? We have two conductive spheres touching each other. It's the same as having one big conductor. Electrons can move anywhere within that conductive material from one sphere to the other because they're touching. And then we separate them in the presence of that charged rod. Now it locks in. Now those excess charges can't go anywhere. One is negative, two is positive. Okay. Coulomb's law. So the electric force let's just think about what might make a difference here. This is the force between two charged objects. So it might depend on the charge of one of the objects, right? We use Q for charge. It might depend on the charge of the other object, right? Might be proportional to that. And because Q, the charge, could be positive or negative, I'm just going to throw absolute value signs in here. Because all I'm talking about right now is the magnitude of my force. What else would affect the force? The distance between those charges, right? And that's going to drop off as the distance gets bigger, the force is going to get smaller. And it turns out it's an inverse square. It goes as this 1 over r squared. Now I want an equal sign here, so I need a proportionality constant, K. K is a constant. And it's equal to 1 over 4 pi epsilon naught. Some books write it that way. Yeah.
I keep getting kicked out from the meeting. Yeah. This has happened 3 times now.
That's strange. I'm not doing anything on my end. Email me, and then maybe in the chat box, see if anybody else had problems. The discussion board, not the chat box, the discussion board on Canvas. Maybe mention it there, see if anybody else had problems, and then email me, and I'll see if I can figure out something.
All right.
Sorry about that.
Thank you.
Okay, so there's our force. Hold on just a second. For some reason, I thought I was plugged in. Hold on. Oh, there we go. I guess it wasn't quite plugged in. Okay, I have power now. All right, so where were we? Coulomb's law. So what I do, of course, force is a vector quantity, right? But because this gets pretty confusing, you could write it with signs and things. What I would do is just use magnitudes only and look at the signs and figure out whether the force is attractive or repulsive and what the direction is. So use this equation to get the magnitude of F and then assign a direction to it based on what you know about charges. So this should remind you of something. Should remind you of the gravitational force that we had in physics 4a, Newton's stuff, yes. There was a constant. The only difference between the force of gravity and the electric force, well, the main difference, I should say, is that there's only one kind of mass, right? So the force of gravity is always attractive, but we have two types of charge, and the electric force could be attractive or repulsive because of that. But other than that, it's right on the same exact situation. Okay, epsilon naught is a constant you'll find in the back of any physics textbook. Mu naught and epsilon naught are two fundamental constants. Epsilon naught has to do with all of our electrostatics equations. Mu naught has to do with all of our magnetics equations, and they're very fundamental constants. But we get tired of writing 1 over 4 pi epsilon naught all the time. So we've come up with this other constant K that just is a little easier to deal with when we're dealing with these types of problems. Okay, so let's do this. If we have this situation, we've got this is my example. Okay. So there'd be a repulsive force here. Two like charges repel each other. So the force would be repulsive, and I'm just going to give it a magnitude of 2. I don't know if you can see the squares on my. I don't know if you can see the squares on my the grid lines here, but I'm going to try to draw these proportional. So I've picked a length for this arrow. I've picked a length that's proportional to the magnitude of the force. Now I want you to draw the forces for these different cases here, based on my drawing. So we're going to pick the same spacing. And we're going to double, this is going to be a plus 2q. So go ahead and draw the forces there on each of those charges on your in your notes. So hopefully you got now that the force is going to be twice as much, right? because we've doubled one of the charges. Let's look back at the force here. If we double one of the charges, that doubles the force, right? So our force is now twice as much. So 1, 2, 3, 4. And the force on this one is going to be, what's it going to be? The same, because these are in Newton's pair. The force that one exerts on the other one has to be equal and opposite to the force exerted on it from the other one, right? They're in Newton's pair. It's a single interaction is causing this force, and so they both feel the same force. Okay, let's do this one. I'll make it minus 2q and plus q. Go ahead and draw in the forces there. So in this case, the magnitude of the forces are going to be the same, right? Nothing's changed in terms of the magnitudes, but the direction has changed now. These are going to be attractive forces. So here's the force on the one on the left, and here's the force on the one on the right. So yeah, let's do this. Okay, I think the problem has been solved. Okay, let's hit the next one here. So we're going to go with the same spacing. We'll have minus q over here, same spacing, and plus 2q over here. Okay. I'll give you another minute to fill these in. So for C here, that's the exact same as the previous one, right? As far as the forces are concerned. So we have a force here and a force here. And then for the next one, the force would be twice as much and attractive. So I've got one that's in this direction and one that's in this direction. Are all Coulomb forces Newton pairs? So this is Coulomb's law, tells us tells us the force between two charged objects. So these would all be Newton's pairs, because a Newton's pair is any force that's from the same interaction, right? So if I have some massive object and the Earth, they are interacting gravitationally, they would be a Newton's pair. The force on the object and the force on the Earth would be a Newton's pair, right? If I have two charged objects and I'm looking at the force between them, that would be an interaction between those two. That would be a Newton's pair. So it's any two that are coming from the same interaction. Okay. Now I'm down here at E. I've got, what have I done? I've doubled the distance. So that means the force is going to be a quarter of what it was in C. So this one is just one grid line, right? And this one is one grid line in the other direction. And now I've doubled the force and it's repulsive. So two grid lines, two grid lines. We okay with that? E is the same as C, except the distance is doubled. And if the distance is doubled, then that means the force is 1/4 as much, because it's 1 over r squared. Okay. All right, let's take a quick look here at our application. So a lot of we see this all around us, right? We rub things together. Every time it seems like I get out of my car, I don't know what Toyota puts on the seats of their car. It seems like every time I slide out of my car and touch the door, I get a shock. You know, taking clothes out of the dryer, simple example, right? What happens in the dryer? Clothes are tumbling around. So you have dissimilar materials rubbing together in a really dry environment, which also helps charge transfer. Plastic wrap, how do you get your plastic wrap to cling on the bowl afterwards when you want to seal up the bowl? Well, it's an electrostatic cling. When you stretch it and put it on there, there's some electrostatic attraction that keeps the plastic wrap clinging to the bowl. Getting that small electric shock from a dog or cat that's walking around carpet or furniture. Yeah, my dog in the car. My dog will move around in the car, and then I get its little wet nose comes up to my elbow, and I get a shock. Thunderstorms, flashes of lightning. We've talked a little bit about that. And then you can use some of this to help prevent pollution in chimneys in big factories. They'll have devices in the chimney that charge the particles, and then they'll have some kind of an electric field that helps them attract and collect those particles before they leave the chimney. And painting cars and things, spray painting, a normal spray can just shoots paint molecules out, and they come out and get on in a small pattern, right? But what they do when they paint cars and have fancy spray painting setups, they'll electrically charge the paint particles as they're coming out of the gun, the paint gun, and they electrically charge the body of the car. So the paint molecules are all charged the same charge. So they fan out because like charges repel each other. They fan out and give you a very nice even coating of paint. And then they oppositely charge the car so that those paint molecules are attracted to the car, and you get much less paint hitting the floor. Most of it ends up on the car. So an interesting application there for painting cars and things. Okay, so we see some of this all around us. Okay, so where are we here? You apply constant charge, like for the spray can, spray paint. You would just have a source of electricity there that is bleeding off electrons onto due to some high electric field, and as the paint molecules come out, they're picking up some of those electrons, and so because the paint molecules you always have new paint molecules coming out, they're picking up new electrons, and you have a source of electricity there. Yeah, so your electric shock is transfer. Yeah, so if you're wearing, it won't work if you're wearing insulating shoes, but if you're wearing like a leather-soled shoes, dress shoes or something, and you walk across carpet and you kind of drag your feet a little bit as you walk across the carpet, then you reach out to touch you're getting charged up as you do that. You reach out to touch a doorknob and you discharge to the doorknob, you get a little shock there. Okay, so let's do this. Actually, we are pretty much out of time here, aren't we? So you should be thinking about applying Newton's Coulomb's law, and look at problems that involve multiple charges. So if you were given charges Q1, Q2, and Q3, would you be able to find the charge there on the force on Q3 due to the other two charges, things like that? Okay, so that's the kind of thing you should be looking at. We'll touch on that next time, and then we'll keep moving forward with electric forces and charges. So I'll stop the recording now. That went all right. A few little hiccups. We'll work them out, and we'll start lab for those of you that are doing the lab today at 12:15. Okay, it'll give you a little bit of time to take a little bit of a break, and the sheet has been posted to the website, so check that out. The worksheet for today's lab. All right, we'll see you next time.
Okay.
Yes, go ahead.
I am not technically